Hello friends, welcome to part 2 of quantum mechanics paper solution, quantum mechanics and application, C-11 paper of 5th semester Dibrugarh University 2022, right? So in the part 1 we have already solved up to question number 2C, right? From question number 1 to question number 2C we have already solved in the first part, and link is in the description box of the first part. Okay, a link of the first part I have given in the description box. So if you want to watch that video, then go to the description box and click the link of the first part. Now you see, so today we're gonna start from this question number 2D. Okay, so before we start, please subscribe to the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. And if you want to follow me on Insta, then this is my Insta ID, that is Oza Lekazit LAKHYAZIT Lekazit 123. This is my Insta ID, so you can follow me on Insta if you want to follow me. So now let's start with this question number 2D, right? So first let me clean these things, just wait. So here what we need to write here, what is Larmor precision, define Bohr magneton. Okay, let me write the answer here. Quick answer to the question number 2D. Answer to question number 2D, right? So here you see an electron moving around the nucleus, around the nucleus of an atom is equivalent to a magnetic dipole. So when the atom is placed in an external magnetic field, the electron orbit precedes about the field direction. About the field direction as axis. This precision is called Larmor precision, right? So what does it mean? Here you see, let me just take the screenshot. Let me go to the next slide to explain this. So in an atom, this is the nucleus, suppose, and here is the electron. Okay, so this behaves like a magnetic dipole. This behaves like a magnetic dipole having north poles and south pole. Okay, so if you keep this atom in an external magnetic field. Okay, external magnetic field. Suppose this is the external magnetic field. This orbit of this electron, okay, it starts to precise about this magnetic field, taking the direction of magnetic field as its axis of precision. Okay, and this precision is called Lomer precision. Okay, so now let us discuss about the next part of this question. Here you see define Bohr magneton. So let me write the answer here. So next we're going to write Bohr magneton. So what does it mean? Okay, so from quantum mechanics, the permitted scalar values of orbital, the permitted scalar values of orbital, right? Let me go to the next page. Values of orbital angular momentum is given by, sorry, let me write R given by L, so small l into L plus 1, here is by 2 pi. So h is Planck's constant, you know, and here small l is the orbital quantum number. This is orbital quantum number, right? So the magnetic moment of the electron, therefore the magnitude of the magnetic orbital magnitude of the orbital magnetic moment of the electron magnetic moment of electron is given by, so it is represented by mu L, right? So this so just what we need to do here, we need to multiply E by twice m, okay, E by twice m with L, right? E by twice m with L. So if that is the case, what are we going to get? E by twice m, instead of L we're going to put this value here, root over L into L plus 1 into E, sorry, not E, h by 2 pi, and that's going to give you the result, that's going to give you that root over L plus L into L plus 1, sorry, L into L plus 1 EH by 4 pi m. That's what we're going to get, right? And this quantity, the quantity so let me write this one here, just wait. Let me write here. Okay, now this quantity, which quantity? E into H by 4 pi m forms a natural unit for the measurement of atomic magnetic dipole moment, for the measurement atomic magnetic dipole moment. Right, and is called, and this quantity is called Bohr magnetron. Right, so hope you have understood this. Now let's go to the next question. So in the next question here it is given that briefly discuss the fine structure in sodium atom. Okay, so let me go to the new slide. So fine structure of sodium atom. So this is going to be the answer to the question number 2. I think this is 2E, right? 2E. Okay, so what we're going to do here, we're going to discuss about the fine structure of sodium atom. Okay, of sodium atom. So sodium atom is alkali atom. So its electronic configuration is, so this is alkali atom. So electronic configuration of sodium atom is given by electronic configuration is 1s2, then 2s2, yeah, 2p6, then 3s1. Okay, so that means, so there is one electron in the outermost cell, right? And so here we must know few terms. So what are things that we should know before we discuss about this topic? So first we must aware of the spin angular momentum. Spin angular momentum, that is, its magnitude is given by root over small s into s plus 1 h cut, right? And here this small s is nothing but spin orbital, spin quantum number. This is spin quantum number. So you must know these things. And now you see, so let me write it properly, right? Sorry. And orbital angular momentum, that is orbital angular momentum, that is given by root over small n2 L plus 1 into h cut, or you can write h by 2 pi, right? Same thing. So here this small l is orbital quantum number, this is orbital quantum number. And due to spin and orbit interaction, spin and orbit interaction, total angular momentum, momentum, that is J, is given by root over small j into small j plus 1, then again is cut. So this small j is total quantum number, right? So hope you have understood this, and here we must know that this small j is equal to L minus S to L plus S. So we must know these things, and we must also know this. So let me go to the next slide. So before we discuss about the fine structure, we must know that S orbital, for S orbital, the value of the orbital quantum number L is 0 and spin quantum number is half, and multiplicity, if you put the value of S here, that's gonna give 2, right? If you put here half, then 2 to cancel, 1 plus 1, that's gonna be 2, and here it's gonna be so L plus S. So 0 minus half cannot be taken here, so we must take only this 0 plus half here, L plus S. So that's why it's gonna be half, and here as we have got multiplicity 2, so we can write 2 as half. Okay, this is the full notation. And for p orbital, the value of orbital quantum number is 1 and spin quantum number is again half, and multiplicity, if you put half s equal to half, then you're gonna get 2, and here in this case L plus S, that's gonna be here we're gonna get L plus S and L minus S, that's gonna be equal to, if you subtract half from 1, that's gonna be half, and L plus S, that's gonna be 3 by 2, right? If you add these two, then you're gonna get 3 by 2. If you subtract these two, then you're gonna get half, right? So multiplicity is 2. So here this p orbital is split into 2p, 3 by 2 and 2p half. Okay, this p orbital, here we're gonna get 2. This is p orbital, here we're gonna get 2p 3 by 2 and 2p 3 by 2 and 2p half, like that. Okay, so hope you have understood this. So now here you see, okay, just do it. So for the d orbital, so its corresponding value of small l, that is 2 here, and s is half, and multiplicity gonna be 2, and here we're gonna get L plus S is 5 by 2 and L minus S, that's gonna be 3 by 2, right? So here we're gonna get, as multiplicity is 2, so we're gonna get 2d 5 by 2 and 2d 3 by 2. That's what we're gonna have. Then now last one, that f orbital. So here what we're gonna get, so for f, the value of L is 3 and spin or quantum number is half, and multiplicity again 2. So here we're gonna get 7 by 2 and 5 by 2, right? So let me write this one 3 by 2 and this is half. Suppose let's make it in this order. Okay, so we must know these things. Now what we're going to discuss here now, fine structure. Let's discuss about the fine structure. Okay, then we also must know that the selection rule is del j, that's equal to 0 and plus minus 1, and del L is equal to plus minus 1 and del s that's equal to 0. This is the selection rule to be followed. So first here we're gonna get 4 series. Then the first series is principal series. This is principal series. And it arises due to the transition okay. So let me write principal series and this it arises due to the transition from NP to 3s. Okay, here n is greater than 2, right? So now for p orbital, so here we have taken NP for p orbital. So if you go back to the table, so this value of L is 1 and S is half and multiplicity is 2, and here we're gonna get 2p 3 by 2 and 2p half, right? So that means, so what we're gonna do here, so for the s orbital L is 0, small s is half, multiplicity is 2, and j plus minus s, j equal to L plus minus s, that's half, and so here we have got 2s half. So that means we can say that transition takes place from NP to 3s. So this is NP. So NP can be written this way: 2p 3 by 2 and another is here 2p half, and transition takes place from NP to 3s. Transition takes place from NP to 3s, and it gonna have two components, right? 2s half here. So it gonna have two components, and what are those? One from this and another from this. Okay, this transition gonna have two components, right? So here first let us check the selection rule. Here you can see that is that followed or not. So now you see, from this 2p half to 2s half, so transition is possible or not. Let me check with the help of the selection rule. Here you see this value of j is half, here also half, and that is difference of j, half minus half is 0. So this is selection rule is obeyed here, and in this case from this to this orbital, this level here 3 by 2 minus half, that's gonna give you 1, right? So selection rule is obeyed, so this transition is also possible. And here you see this is p, this is s, so difference in L. So for p, L is equal to 1, for s, L is equal to 0, right? So 1 minus 0, that's going to be 1. So that's why this selection rule is also obeyed. And here you see del s should be 0. Yeah, here obviously 0 here, because the spin quantum number for both p and s here half, right? So half we have already got in this table. Here you see, right? So now just wait. Sorry. So this is the principal series. Okay, So now let's discuss about the next series, that is our SARP series. It arises due to transition from here ns to 3p, ns to 3p, and here the n is greater than 3. That means n should be equal to 4, 5, 6 dot 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 so on, right? And here in this case n should be equal to 3, 4, 5 dot 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 so on, right? So let me take a new slide. So now let's discuss about SARP series. SARP series. So it arises when transition takes place, when transition takes place from ns to 3p, where n is equal to 4, 5, 6, 7 dot 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 so on. So here you see, for this s orbital, so we know the value of L is 0, spin orbital quantum number is half, and the multiplicity is 2, and J plus I is half here, and so full notation is 2s half. So here this is the ns level, right? This is the ns level, 2s half, right? So now let's draw the 3p level. So 3p, so for p level, here you can see, so value of L, that is orbital quantum number, is 1, and the spin quantum number is half, multiplicity is 2, and L plus is this, and L minus s is this, right? So that's why the full notation should be multiplicity. This one is multiplicity, and this is L plus s, this is multiplicity L minus s, that means j, value of j, right? So now that's why, as we have got two levels here, one is 2p 3 by 2 and another is 2p half. So this p level splits into 2, that is 2p 3 by 2 and 2p half, right? Let me draw this way. Okay, so now here transition takes place from this ns to 3p, and it must have more components. So in order to get that, in order to find that, we must follow the selection rule, that del L is nothing but plus minus 1, and del J, that is 0, either 0 or plus minus 1, and del S is 0, right? So here you can see that so spin quantum number in both cases same, so half, so definitely it is 0, and here you see transition allowed from this level to this one and this level to this one as well, because del J in these two cases, half minus half 0, which is allowed. Then here you see, then these two cases, this one and this one, half minus 3 by 2, that is minus 1, that is also allowed, right? And del L is plus minus 1 here, del L is plus minus 1. For S, L is equal to 0, for P it is 1, so difference is 1, So that's why these two are the components of this transition. Okay, so hope you have understood this. So now let's move on to next series. So that's going to be diffuse series. Okay, let us discuss about diffuse series. So let me clean this first. Okay, take the screenshot. Okay, now let us discuss about diffuse series. Okay, next one is diffuse series. Diffuse series. So this series arises due to transition from your ND to 3p, where n is equal to 3, 4, 5 ... and so on, right? So again, from the table, first let's make it ND. This is ND. So how many levels here we're gonna get, into how many levels it gonna be, it gonna split into how many levels? Let me check. If you see the table that's shown before, here you see. So for D, value of L is 2, that's okay. Small s is half, and multiplicity is 2, that's why here we're gonna get 2D, 5/2 and 3/2, because here L plus S is 5/2. So this is L is 2 and S is half. If you add these two, then you're gonna get 5/2, and L minus S, that is 2 minus half, that's gonna be 3/2. So that's why we are getting here 2D 5/2 and 2D 3/2, right? So hope you have understood this. So that's why this d orbital splits into these two sub levels, you can say. Okay, so now similarly for 3p, so we have already discussed about p level, right? So it also have two sub levels like this. Here we have 2d 5/2 and 2d 3/2, and here we know that 2p 3/2, that we have already discussed in sharp series, right? 3/2 and 2p 1/2, right? So we have already got discussed this in sharp series. Okay, so again, if we follow this selection rule, z is equal to 0 or plus minus 1, and del L is equal to plus minus 1, and del S is equal to 0. So for n and p, both spin quantum number in both cases half, right? So that's why half minus half 0. So transition from this level to this level is allowed. So that's why, just wait. So let me show you the transition of this components of this transition. So here you see, first let us take this level and this one. So here this one 5/2 and 3/2, if you subtract these two, then you're gonna get 1. So del z, that's plus minus 1. So that's why difference of these two is equal to 1. That means transition between these two levels is allowed according to the selection rule. This is one component we have got. So now let me check if the transition possible between these two or not. So here you see 5/2 minus half. 5/2 minus half, that's going to be 4/2, that's going to be 2. So 2 here, difference in z is 2 not allowed here, only plus minus 1 and 0 allowed. So transition between these two levels is not allowed. So now let's check transition from this one to this one. So here you see 3/2. If you subtract 3/2, so del z is 0, that is allowed here. Then in case of L, value of value of L in D and P, in value of L in P is 1, and value of L in D is 2. If you subtract 2 and 1, if you find the difference, that is 1, so this is allowed, this transition is allowed. So here we don't need to check about the del L, right? So now here we are going to check only these numbers, that means J, okay? So angular quantum number, so we're gonna check the difference is either 0 or plus minus 1 or not, okay? If we don't get the difference of these numbers between any two levels is equal to either 0 or 1, then transition will not be possible. So here let me check the transition between these two levels, is that possible or not. So here you see 3 by 2 and half, their difference is 1, okay? So that's why this transition is also possible. So here we are getting 3 components, okay, triplets. So hope you have understood this, right? So now let me clean this. Let me take the last series. Let me show you the last series, that is fundamental series. Let's discuss about fundamental series. So now we're going to discuss about fundamental series. So it arises due to transition from NF to 3D, okay, NF to 3, NF to 3D. Here you see, so this is the NF and 3D, this is the 3D. So transition will from this one and this one will be possible because del L should be plus minus 1, and for F L is equal to 3, and for D L is equal to 2, so difference is definitely 1 here. So that's why this transition is possible. Now let me go the sub levels. So here you see, let me check the table. In this case here you can see, so here you see this is multiplicity 2, and L plus S is 7 by 2, that is equal to J, and L minus S is 5 by 2. So here we are getting 2 F 7 by 2 and 2F 5 by 2, 2F 7 by 2 and 2F 5 by 2. And we have already discussed in the last series, in the diffuse series, that the two levels of this 3D, that should be 2D 5 by 2 and 2D 3 by 2. Now let me check the components. So these are the selection rules that we are to follow. So here you see in both for both cases D and F spin quantum number is half, so that's going to be 0, so it's this rule is obeyed here. And let me check the transition from this top level to this one. Okay, here you see in this case 7 by 2 minus 5 by 2, that's going to be equal to 1, so that means del J is 1 in this case. So this transition is possible here, this transition from this level to this one is possible. So next let me check this one and this one. So 7 by 2 minus 3 by 2, that's equal to 2, which is again greater than 1, right, greater than 1. So transition from this one and this one not possible. So now let me check the transition between this one and this level. 5 by 2 minus 5 by 2, that's 1, so sorry, that's 0. So 0, del J is 0, that is allowed, okay. So then transition between these two, let me check this is allowed or not, okay. So here you see 5 by 2 minus 3 by 2, that's 1, so it's allowed, right. So this is the last. So our next question is to F. State the basic differences between Passenbeck and Stark effect, okay. So let's write the answer. So Passenbeck effect is, now let me write the definition here. This is what Passenbeck effect, okay. And let me write about the Stark effect here. So this is the definition of Stark effect, and if you write these 2 points, this pass and back and this is a Stark effect, then that's enough for the difference between these two, Stark and pass and back effect. Take the screenshot of this pass and back effect, and this is the Stark effect. So this was the answer to the question number 2F, right? So now 3A. So I think I have already explained this in another video. I'm going to provide the link in the description box. I'm going to write question number 3 answer, then I'm going to provide the link here in the description box, you may check. Okay, now let's move on to 3B. Okay, and the next question we are to solve here, 3B. Write down the wave function of ground state, okay, 500 of hydrogen atoms. So the representation of probability densities of S, P and D cells. So first let me answer this question 3B. So what we are asked to write here, the wave function for ground state, phi 100 of a hydrogen atom is given by phi 100 is equal to 1 by root pi z by a naught whole to the power 3 by 2 e to the power z r by a naught, right? Here the z is atomic number, a naught is equal to h square epsilon naught divided by pi mu e square. Here mu is reduced mass, and here r is the separation between the nucleus and the electron. That means you can say radius, separation between electron and nucleus, right? So this is the function that we need to write. Okay, so now let's discuss about this second part of this question, the polar representation of probability densities of SPD cells. With the help of diagram we need to draw. Okay, so now let me take the new slide. Here you see, so in polar form, here you see we can write this wave function of one electron atom. Here we can write psi, so write these things as well, psi of r comma theta, just wait, r comma theta comma phi. It can be written as a, it can be expressed as a product of three functions, capital R, which is a function of the small r alone, then Q, which is a function of theta alone, and F, which is a function of phi alone, and then this is in polar form. Okay, in polar form, right, in polar form. So please complete this one. Okay, and here you see, in this case the probability density, this phi mod square, this probability density is given by this, right? And here you see we are asked to draw this diagram representing probability density for S and P and as well as D. So here we have, this is this graph is for 1s, right? This is for s orbital, and this is 2s, right? And here you see this red one, this one is 2p. So let me draw the for 3d d orbital. Okay, it should be like this. Okay, for d orbital I'm gonna draw in black ink. This should be the graph, right? This represents the probability density of 3d. Okay, so this is the answer to the question number 3b, second part. Okay, and this is the answer to the 3b of first part of the 3b. Okay, so what is the next question? Question number C. What are the orbital quantum numbers, and write down the values of these quantum numbers for S, P and D. Okay, let's answer this question as well. So now let me give you the answer of question number 3C. Let's here the question is, what are orbital quantum number and magnetic quantum number, and write down the values of this quantum number for S, P, D cell. Okay, so here is the answer. This is the definition of orbital quantum number. So we know that magnitude of orbital angular momentum is this, and here this small l, here you can see the quantum number, this is small l, determines the magnitude of orbital angular momentum is called orbital quantum number. So let me clean this. Okay, so this is the definition. The quantum number which determines the magnitude of orbital angular momentum is called orbital quantum number, and value of this quantum number for S cell, P cell and D cell are given here. Okay, so now let us discuss about magnetic quantum number. So now you see the component of the orbital angular momentum, that L, in the direction of applied magnetic field. So if we have applied the magnetic field in z direction, then Lz is given by ml h cut. So here this ml is the quantum number which determines the component of the orbital angular momentum along the applied magnetic field is called magnetic quantum number. So now let's see what are the quantum numbers for S, P and D cell. So here you see, as I have already told you that for S, P and D, these are the orbital quantum numbers. So now if you know the orbital quantum numbers, you can find the magnetic quantum number very easy. If L is 0, then ml is 0, magnetic quantum number is 0. If L is equal to 1, then ml will start from 0, and one value should be plus 1 and another should be minus 1 when L is 1. If the L is 2, then ml, you're gonna get 0, then you're gonna have plus 2 and you're gonna have minus 2, right? That's how we determine. Sorry, one more thing, I forgot this to write 1, and this is minus 1. Okay, minus 2 minus 1. Okay, so here is the answer, right? When L is equal to 1, then magnetic quantum number is 0, plus 1, minus 1, right? Okay, when 2, then 0, when L is equal to 2, then ml is 0, 1, 2, then minus 1, minus 2. That should be minus, okay, right? Take the screenshot. Okay, this should be minus 1, right? So thank you for watching. See you in the next video. Remaining questions will be solved in the next video, right?